Hello dear students, in this video we are going to see about bottom-up parsing in compiler. We are first going to see about the introduction, and then we are going to see about LR0 and SLR1 algorithm in bottom-up parsing. So you might be wondering many times whenever you do compilation in any programming language, have you ever thought about how the compiler will understand the code is correct and the code is incorrect? For example, if you consider in Java, this instruction is correct, but this instruction is not correct. How does the compiler will understand this is correct, this is not correct? This is all because of this parsing. So this is the second phase of the compiler, also called as syntax analysis. So what is actually the parsing means? It will check whether the given input string can be generated from the given context-free grammar or not. What is a context-free grammar? It is the rule of the programming language. So that process is called parsing. There are two types of parsing, top-down parsing and bottom-up parsing. So in this video, we are going to focus on bottom-up parsing. So what happens in the bottom-up parsing is, for example, you consider there is context-free grammar. Let's say S derives A, and A derives small a and capital A, and A derives B. And the input string is BAB. So since it's a bottom-up parser, so what is actually it's happened means it will check whether we can able to generate this string from this context-free grammar or not. So for that, what does it do means it will find the suitable grammar for this input string. For example, B, if you say in this grammar, B can be derived to A, and B can be written as A. And this A can be written as C, A, small a, and capital A can be written as capital A. And this capital A and this capital A can be written as yes. That is the starting symbol. So from the input string, if you could able to come and reach the start symbol, so this is the starting symbol. If you could able to reach it out, then we can say this is a correct input string and this is out of any syntactical error, and the parsing is successful. So we have to find which rule can be generating this input string. So for example, we found that this grammar A derives small b is a grammar which could able to generate this input string. Finally, doing each and every step, we reach the starting symbol. So this is what called as bottom-up parsing. From the input string, you have to reach the start symbol. So this is another example. And the exam in bottom-up parsing, we have LR parser. What is the meaning? There are many different types of bottom-up parser are there. We are going to discuss about it. What is this LR parser means? L stands for left to right input scanning, and the second, the R represents the rightmost derivation in reverse. So that's what we saw, right? Rightmost derivation in reverse. And now there are many different types of bottom-up parsers are there. Actually, if you see the bottom-up parser, if you see this, we have many algorithms like LR0, SLR1, and then we have LALR and of 1, and then CLR of 1. So these are the algorithms, some of the algorithms present in this bottom-up parser. So in this video, we are going to discuss about these two algorithms. And what is LR means? As we know, it is left to right input scanning, rightmost derivation in reverse. Here it is 0 since we are not going to do any look ahead. This is the least efficient algorithm in the bottom-up parser, and the most efficient algorithm is the CLR, which is canonical LR. One represents there will be one look ahead. What is this LALR means? Look ahead LR. And this SLR means symbol LR. So these are some of the important algorithms, and this is the least one and this is the most efficient one. As I told you, LR parser will not have any look ahead. So it will do any decisions based on the current state. And the next one, it will be using a parsing table. In the parsing table, we will be using a canonical LR items. And I'll tell you what is item and all these things, which is, for example, if we are in the LR0 parser, we use parsing table. It will be created from this LR0 items, and which is derivated from the grammar rule. We'll see all the example. So, for example, you can see if, as I told, there is grammar like this means. So, what is an item? Is derives dot AA. So, when I put a dot in front of it or anywhere, so this is an item, this is also an item. So, what does this dot represents? It have not seen any of the symbol here. Here, this dot represents it has seen the first A and the second A is yet to read. So that is the meaning. For this, all this algorithm, we'll be using this parsing table. This parsing table can be generated from the canonical LR0 items. We'll see within some few minutes. And this LR0 is least efficient. No, why? Because it has lot of conflicts within it. What does the conflict mean? For example, when you construct a parsing table, if you have seen the top-down parsing, you know what is the parsing table. So we have all the states here, and here we have action and go to. So in a particular place, in the action, you have all the terminals like A, B, dollar, and in the go to, we have all the non-terminals like S and A. So in one place, if you can, we will be having shift, and we will be sometimes we have a reduce and all these things. So what does this conflict means? In one place, in this place itself, you have shift as well as the reduce in the same place. So here you have shift, two types of reduce. So this is the conflicts. So two types of actions are suggested in this place, which means shift is also suggested, reduce is also suggested. This is called as conflict. So it doesn't know whether should I shift or should I reduce. And here also we have a conflict called reduce conflicts, which means it is suggesting more than one grammar rule to use. So it will not know correctly which grammar to use to reduce. So this is a problem in the LR0 parser, that is the conflicts. So that is why it is considered to be the least efficient bottom-up parser. So the problem is shift reduce. What is shift reduce? In a particular action, same place. So in the zeroth state, for example, with the input small a, it has two actions to be considered, shift as well as reduce. Here, we in the second state, we have it is suggesting two grammar rules to reduce. So it doesn't know whether to use the second rule or the third rule. So these are the conflicts. So to avoid this only, we are going to the next algorithm called SLR of one parser. So the one more problem here in LR0 algorithm is it doesn't do any look ahead. That is why it is zero. It is blind about the future. It doesn't consider any look ahead. So to avoid all this problem, in the SLR1 parser, SLR means symbol LR1 parser. So symbol LR with one look ahead. This one represents one look ahead, which means one symbol will be looked ahead to take any decisions. So because of this, we can avoid the problems of shift reduce conflicts or reduce conflict. And so we can be very confident about a particular step, whether to shift or to reduce. And so this we'll be seeing all this example. And this bottom-up parser with LR parser, bottom-up parser, we are using this LR parser, no? So this LR parser is used in the real-time compiler also, like GCC compiler, Java compiler. So all these compilers are using this bottom-up parser, that is LR parser. And also I told you the least efficient is LR0 and the most efficient algorithm is CLR1. Okay. So in the bottom-up parser, we are going to use two main strategies. One is shift, another one is reduce. What is shift means? You are supposed to read the next symbol. So read the next symbol. That is the meaning of shift. What is the meaning of reduce means? You are, for example, you are looking at an item on the top of the stack, which means, for example, we had no A, we have a production like this. So in the string A, so when B is there, this B can be reduced to A. Right? This is what reducing, which means we have seen all the symbols in the right hand side. So the right hand side symbol can be now reduced to the left hand side. So this is what the right hand side, and this is what the left hand side. So when all the symbols in the right hand side is red, that can be reduced to the left hand side. So this is what the reduce. So these two strategies are used in this bottom-up parser. So what is the main goal in this? We have to repeat this process. In the previous example, I told no A B is the string means. So we have to repeat this process. This can be reduced to this, and this A and this A can be reduced to this, and this A and this A can be reduced to this. So this should be repeated until we are reaching the root node, right? So that is the main goal. So we have to repeat until you are reaching the starting symbol. So if you could able to reach the start symbol, then that code, that the input is a valid one. That is the meaning. Okay, so now let us go into the algorithm. This is the introduction about the bottom-up parser. So now let us discuss about the first algorithm, LR0. By the time we will also see SLR1. There is only a small difference. Some of the terminologies used in this LR algorithm is first one is item. So what is an item means? For example, consider I am going to use the same grammar. This is a grammar, right? A derives A and A derives B. This is the CFG, context-free grammar I am going to use. So here this totally we call it as context-free grammar, and each one of this is called as production. So what is an item? When I take a production, when I add a dot before it, this become an item. Actually, this is a production, but when I add a dot before it, it is an item. So this dot can be in this place as well. So if I have the dot in this place, the meaning is I have not yet read any symbols yet. So when I put the dot in this place, the meaning is I have read one symbol and I am yet to read the another symbol. So, and for example, and when I put the dot at the last means, the meaning is I have completed reading all the symbols. So that is, we can say it is a final state. So this is the meaning of item. So when I add a dot in the production, in the right hand side, stating whether I have read all the symbols or not. So when you add this dot, the production is called to be as item. And the next thing is, the next important terminology here is closure. So what is closure means? Here I have given an example. If I have an item, this is an item because this is a production, but when I add a dot there, it become a item. So before after the dot, if you have a non-terminal here, who are all the non-terminals in this production? All the left-hand sides are all the non-terminal. S and A here in this case. Who are the terminals A, B, and also we can consider dollar because it is denotes the end of the string. So here, whenever after this dot, if I have a non-terminal, then I have to expand all the productions of this A. So for example, you consider here, I have, this is my, if you consider this is my production, and now it is an item. After the dot, I have a non-terminal. So then what should I do means I have to write all the productions of A. So what are the productions of A? A derives dot A and A derives B. So when I write this both, which means I write all the productions of A with the dot, okay, in the beginning. So this is the closure of this one. So you now read if item expects a non-terminal next. So this is expecting a non-terminal. After the dot, we have a non-terminal. We must include all the possible ways the non-terminal could be derived. So what are the ways A can be derived? So A can be small a and capital A, and A can be small b as well. So this is small b. So this can be like this. So A can be in this expected in this both ways. So when I include all the expected way of this A, possible way of writing this A, this is said to be as closure. So for this production, this item, this are the items. Sorry, these are the closures. So closure means expanding the item. When dot is before a non-terminal, include all possible production of the non-terminal. So you have to write all the possible productions of this non-terminal. That is called, so it is called as closure. And the next important terminology is canonical collections. What is canonical collection means? All the possible state you can reach by shifting the dots. So this dot is here in the beginning. Next time after reading the small a, this dot will be coming this place. And after reading capital A, this dot will be coming here, right? So by doing all this, we have lot of states. So all the states together, we call it as canonical collections. Now let us take an example and we'll work so that you'll be clear about all this. So first, we are going to discuss about LR0. By the time we'll also learn about SLR1. Okay. So both are very simple. For this, let me take the same example. S derives A and capital A derives small a, capital A. And capital A is also deriving small b. So consider this as our example. And this is the context-free grammar. So here, so what is the main purpose? This is the parsing algorithm. What is the purpose of parsing algorithm? Whenever input is coming, which means here it is instruction from a programming language. We have to understand whether there is a syntactical error or not. So we have to check this, right? That process is called parsing. To check this, we have this algorithm. So this is one way of checking whether the input string is free from the syntactical error. So to do this process, with the help of this LR0 algorithm, the first step is you have to augment a production. So first, that is the first step. So here, who is our starting symbol? Yes, right? So we have to bring this yes to the right hand side, and the left hand side introduce a new non-terminal. This is the first step. Sometimes you consider this is my example production means E derives E plus T and T derives T into F, something like this you consider for example. So if this is my context-free grammar means, what is the first thing you have to do here? This is my starting symbol. So for the starting symbol, you bring the starting symbol to the right-hand side and introduce a new non-terminal. So only one production we are going to augment. Okay. So this is the first step. So for this example, this is the only production we have to include. So this is the first step. After you include this first step, we are going to start our algorithm. So how to start this? Let me consider the first state. Let me call it as canonical item set of I0. Okay. So when I started, use this augmented production and S derives and make it as an item. So add with dot in the beginning. So this is the what we have added, one production we have added. Start with this production only. When you start, put a dot in the beginning, right? So this is how we have to start. If you are doing here, how will you start? E dash derives dot E. Likewise, for this grammar, you will do like this. Okay, now we are going to work on it. Let's do that. And now what is now we have to find the closure. What is closure? We have discussed after the dot, if you have a non-terminal, and then you have to write the all productions of A, right? So here, who is our production? These are all our production. So after the dot, we have a non-terminal S. So you have to write the productions of S. So what is the production of S? S derives dot A. Whenever you add any production, started with dot. Now you see, after the dot, what we have? After the dot, we have a as a non-terminal. So now I have to write all the productions of A starting with dot in the beginning. So these are the two productions of A, right? So now for this after the dot we have a non-terminal S. So we wrote because in this question we have only one S production. So I wrote one. After I writing this, I can see that after the dot again there is a non-terminal. So I wrote only one symbol. Okay. So for this dot A, I have written all possible predictions of A. Start with a dot in the beginning. Now if you see after the dot there is a terminal. Here also after the dot there is a terminal. So for terminal we don't have any predictions, right? So that's it. So this together we call it as canonical item set of I0. Okay, so this is the first state. Now let us go to the next. So next state. So here if you see in this first production, who is now ready to read at a time we can able to read only one symbol, that you have to keep in mind. So before see here dot is here. So the next who is ready to read? Yes. So when I put yes, read yes. So after I read this yes, the dot will go after this. And now look at here. Is there is any other production with to read yes? Nothing, right? So that's it. So it is over. So this one I can call it as item, canonical item set, um, canonical item for I1. Okay. Now who is the next thing to read? A, capital A. See here. After the dot, who is now ready to read now? A, capital A. So when I read this, it becomes S derives A dot. This dot will come to the next place. See, this dot will come to the next place here. At a time, we can able to read only one. And if you see here in this canonical item set, there is no other item with A to read, capital A to read. So we will stop it here. And now look at here carefully. After the dot, there is a non-terminal. So this is, we have to write the closure of this. After the dot, whenever you have a non-terminal, write all possible productions of it and make it as an item. So for A, we know that there is two productions, A, capital A, A derives dot B, right? And now if you see after the dot here, it is small a and it is small b. So those are the terminals. So nothing to do with it. So we will stop it here. So this is over. Now this is canonical item set 2. Now look at here in the item 0, canonical item set of I0. Who is the next thing to read? Small a. So when I read this small a, it is like A derives small a. Then the dot will come here after reading the small a. And now if you see after the dot, you have a non-terminal. So we know after the dot, if you have a non-terminal, write all productions of A. That is the closure. So it is like A derives dot A and A derives dot B. Right? So now after the A, here it is a small a, here it is a small b, which is a terminal. So nothing to worry about it. There is no closure for it. So that's it. So we can finish this and let me name it as I3, canonical. And who is the next thing to read here in the I0? B. So when I read B, it is like A. After reading B, the dot will come this side. So for this, let us name it as I4, right? So that's it. So in the item 0, we have read all the symbols one time. Here we read S, here we read A, here we read small a, here we read small b. Hope you have got it, right? So what is the next thing here we have to do? So come to the next state, I1. Is there is anything to read here? Nothing. So we don't have to worry about it. And this is called as final state because we have read everything. And now if you see here in this I2, who is the next symbol to read? Capital A. So when I read a capital A here, so it is like S derives A, the dot will come to the next place. And if you see here, check it once again here, is there is any other item to read capital A? Nothing, right? So we will finish it here. So the next item is I5. And next, who is next person to read here? A, right? Here the next is small a to read. So when I read it, it is like A derives A, the dot will come here and capital A. And after the dot, there is a non-terminal. So we have to write all the productions of A as an item. So A and A derives dot B. Now look, listen here. All this is same as this, right? See, all the three items we have here is same as this. So we don't want to write it once again, right? So instead of writing all this once again, what I will do is I will just use the name of this. Okay. So here I will write as I3 because when I read A, I'm getting the same items only. So instead of writing it again, I'll just put the name of this item as I3. And listen here, when I read this B, I will get the same item, right? So what will I do? I'm going to write when I read B, I will get I4. Okay, and next here, come here. So I3 is over. Now come to I2 is over. Come to I3. And who is the next thing to read here? Capital A. So when I read capital A here, it becomes A, capital A, and the dot will be coming here. And look at here. Do we have any other A's to read? Capital A to read? No. So we will finish it here and name it as I6. And here, who is the next thing to read? Small a. So when I read small a, I'll get same thing again. Same set of production will be getting. So I put it as I3. Same thing only I'll be getting. And when I read the small b, I'll be getting I4. Right? So that's it. So I3 is over. Now come to I3 is over and come to I4. If you see in the I4, nothing is there to read because everything is read. Come to I5, nothing is there to read. Come to I6, nothing is there to read because we came to the end. So this I5, I6, I4, I1 are all called as final state, which means we have read all the symbols in the right hand side so that it can be reduced to capital S. This is the meaning. So we have now found all this canonical collections. What is canonical collections now? All possible states. So these are all possible states you can reach by shifting the dot. I hope now you can understand. Starting from the augmented grammar. Who is the augmented grammar? This is the augmented grammar. So from the using the augmented grammar, we have found all the states. So this all together called as canonical collections. Now, what is the next important step is we are going to make the parsing table. That is a very important thing. Help us to do the parsing. So how to construct the parsing? In the canonical collection, you have to see how many states are there. So it is starting from 0 and it goes till I6, right? So you have to write all the states 0, 1, 2, 3, 4, 5, 6. And now here we have two more things. One is called as action. What is the action to be taken? And the next is called as go to, where to go. So in the action side, you have to write all the terminals. Who are all the terminals in this grammar? So I'll write the grammar here once again so that it will be easy for you to look at it, right? So our grammar is S derives A derives small a, capital B, capital A, and A derives B. So these are our context-free grammar, right? So if you look at this context-free grammar, who are all the terminals? So our terminals are A, B, and you should not forget about the dollar, which says the end. And after that, we have to write find go to. What is go to means? In the go to, you have to write all the term. What is that? Non-terminals. So what are the non-terminals? We have here S and capital A. So if you see in the left hand side, these are the non-terminals. So S and capital A. You can easily note it out. Now let us start doing filling this parsing table. Now we'll go by state. If you now first zeroth state. Come to zeroth state. From the zeroth state, where are all we are going? One is from the I0, we are going to the with the help of capital S, we are going to the state number 1. So I0 on S, we are going to state number 1. So fill 1 here. Okay. Now you see in the item 0 on capital A, it is going to 2. I2. So put 2 alone, the number alone. Now, what is the next thing? From the item 0, it is for small a, it is going to I3. So here you have to write S3. Don't write the number alone. For the terminal, this side you have to write as S3. What is S3? 3 is from this number. S is means shift. Shift means read the next symbol. If it is finding A, which means okay, there is no production with single A, so you have to read the next thing. That is the meaning. And now I from item 0, when I use B, it is going to 4, I4. So here I have to write shift to 4, which means read the next symbol. That is the meaning. And that's all. So it is going with 4 symbols outside. So we finished all 4, right? So now let us go to the next state. And when I look at the next state, 1, it is a final state. And that too, it is a augmented production, right? So for this augmented production alone, when it comes to the final state, what you have to do is for the state number 1 on dollar, because after we finish, when you reach the root node, after that it is the end of the input, right? So you have to say the end. That's it. Accept. So whenever we are from the bottom, when you come to the start symbol, that's it. It finished. So to denote that for this final state, which we have augmented for this alone, I have to write 1 on dollar as accept. Right? 1 on dollar as accept, which means we completed. Okay, hope you have understood. This first state is a final state because the dot is in the last. And that too is a special augmented production. So for this alone, in the state number 1, on dollar, we have to write accept. And there is no other production. So come to the next state, I2. So when you see in I2, again we have to see the go-tos. Where are all it is going. So from the state I2, it is going to capital A. It is capital A with the I2 is going with the capital A to I5. So write I5 here. So in the go to part, write the number alone, 5. And then from this item state 2, on small a, it is going to I3. So small a means this side. So here you have to write a shift 3. Similarly, if you see here on B, it is going to I4. So write it as S4. Look at here, is it going to anywhere? No, right? So that's it. So the state number 2 is over. Now let us go to the next state. State number 3. So here again you have to see from the state number 3, it is going to, on A, it is going to I6. So write 6 on here. And see on item 3, on small a, it is going to I3, small b, it is going to I4. So here you have to write it as S3 and S4. So state number 3 is also over. Now we have to go to the next state. That is our 4th state. See the 4th state. This is our 4th state. See, 4th state is our final state, right? And it is a normal production. So for this, since it is a final state, we have to reduce. Which means what? See, we have seen B. So we can see the B can be reduced to A. So since it is a final state, write R. Okay. So in all the terminals, you have to write R. And what number should you write means, what number you have to use? You have to number all these productions. This as 1, this as 2, and this as 3. And A derives B is which number? 3. So here we have to write as R3, R3, R3 in all the terminals. Okay, so I'll repeat. I4 is the final state. So look at the number of this production, that is 3. So since it is a final state, we can reduce it, which means B can be reduced to capital A. So saying it can be reduced using the third production. So that is what R3, R3, R3. Okay, then next, what is the next state? State number 5. So we are going to do for the state number 5. So if you see for the state number 5, again it is a final state because we have read all the symbols. So if it is a final state, what you have to see the number of the production. That is 1. So which means A can be reduced to capital S now. So we have to use R. Yeah, whenever we have a final state, use reduce. So what I have to write in the state number 5, use R1, which means that production is 1, right? So we have to write R1 throughout all the places. R1, R1, R1. Now we are discussing LR0, okay? So what is the last state, I6? Here it is again a final state. What is the number of this production is 2. So in I6, we have to write R2, 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 all the places. R2, R2, R2. R means reduce. R means reduce. S means shift. Shift means go to the next symbol, read the next symbol. That's the meaning, right? So this algorithm is called this way of doing is LR0. What is LR0? Here 0 means we are not going to look at we don't know about future, any symbol. Just looking at the current state, we just fill all this, right? This is LR0. Already we saw LR0 have a problem of conflict. Shift reduce conflict and reduce conflict, right? So this is a least efficient one. So what we are going to do is we are going to the next algorithm. I told you, no, other algorithm, SLR1, that is simple LR1 algorithm. So here there is a small change between this LR0 and SLR1. So this table itself we are going to do it. What we are going to have to do here is, first of all, we have to find all the follow of all the non-terminals for this grammar, in this grammar. So first we are going to find the follow of yes. What is follow of yes? Blindly we can add dollar. And now we have to see in the right hand side anywhere S is coming? No. So that's it. Follow of S is only dollar. Now we have to find follow of capital A. So if you see here in this production, for A, who is following it? Another A. So we have to find the first of this A. So if you see first of A, this is A, and the first of this production is B. So here we have A, comma B. Okay, now come to this A. So after this A, nothing is there. So you know the rule how to find the follow. If nothing is there, it's just epsilon. So then you have to find the follow of the left hand side. What is there in the left hand side? Capital S. What is the follow of yes? That is dollar. So dollar will also come here. Now look at this A. Who is following? Nothing. So you have to find the follow of A. Already we are finding follow of A only. Nowhere A is coming. So follow of A is, that's it. Now, with the help of this SLR1 algorithm, what is the difference is, see here, in the final state, what happened in LR0 algorithm, blindly we wrote reduce everywhere. But in SLR1, we have to find the follow of the left hand side and you have to write reduce only in that place. So let us go one by one. So where is reduce happening? From the fourth state. So here in the fourth state, what is in the left hand side? A. So you have to find what is the follow of A, B and dollar. So in the place of A, B and dollar, we have to write R3, R3, R3. Already it is like that only. So no change here. Now come here for the fifth state. So fifth state, we have to see what is the follow of left hand side, that is A. What is the follow of yes? Dollar. So what we have to do is, here only in the dollar we have to write R1. Okay, so that is what the this is how it is improving from the LR0, SLR1. So SLR1 is improving from LR0 algorithm. It is not going to blindly write reduce in everywhere. Instead, it is going to look at the follow of the left hand side, and then in that place only it is going to do the reduce. It is going to look ahead and it is going to do it. Now the sixth state. This is the sixth state. What is the follow of A? For here, you have to find the follow of the left hand side. So that is A. So what is the follow of A? A, B dollar. So here is also in A, in the B, and in the dollar, you have to write R2. Why it is R2? Because this production number is second production, no? So we have written R2. Why we wrote in everywhere? Because in the follow itself, we have all the symbols. That's why we have written. This is the only difference between LR0 and SLR1. Got it? So SLR1 is efficient when you compare to LR0 algorithm. And now parsing table is over. Now we are going to do the parsing. So what is mean by parsing? In the parsing, we are going to take an input symbol. Let us take BAB and we have to check whether this can be derived from this grammar, which we have taken as this is our grammar, right? So we have to check whether this thing can be derived from this context-free grammar or not. So we are going to do the parsing. So what you have to do here is, one is we are going to use options like stack, and then this column is for our understanding. I'm going to use symbol, and then here we are going to use input string, which we want to check, and here we are going to say what is the action I'm going to take for it. So this many things you have to find it. And who is our, okay. So now in the stack, initially in LL1 algorithm, that is top down, we will be initializing the stack in the bottom is dollar. Here you have to initialize with this first state. Who is the first state in the canonical item? I0. So initialize with this. And here you have to initialize with dollar. Here you have to write the input string. At the end, you have to put a dollar to say the end of the input string. Now you have to say, with the help of the parsing table only, you can do the parsing. So parsing table is very important. How can you construct the parsing table with the canonical items? Okay, now we have to see 0 on the stack, we have 0 on B. First input is B. So look at the parsing table, 0 on B. What is the action we have to do is S4. So S4. What is the meaning of S4? S means shift. So shift means what I told, go to the next input. So I'm going to shift this B to this shifting, and I'm going to read the next one. So write only the remaining and push this 4 to the stack. 0, 4. So shift means what you have to do. Shift means read the next input. So I'm shifting this to the next place. So it become AB dollar. So just for understanding, I'm shifting this B here in this place. Now look at who is in the top of the stack. 4. 4 on A. What is 4 on A? See, 4 on A is R3. So 4 on A is R3. That is the action. What does R3 means? The third production, right? So if I number it, 1, 2, 3. So write the third production, this one. So R means reduce, no? So actually here we have a dollar. So reduce means what now? This B can be now reduced to capital A. So I have reduced to capital A. What are the other things we have to do is see in the right hand side how many symbols are there? Only one symbol is there. So what you have to do? Reduce one symbol here. And down now you see who is in the top of the stack? 0 on left hand side. Yeah, 0 on A. What is 0 on A? 0 on A is 1. See, sorry, 0 on A is 2, right? See, 0 on A is 2. So I have to write 0, 2. Got it? So these things you have to do. Now who is in the remaining in the input string? A, B, dollar. Got it? So reduce means, this is for understanding, this is how it happened. B is reduced to A. And now if the right hand side have one symbol means take away 1 from the stack. Who is in the top of the stack now? 0. 0 on the left hand side, A. So 0 on A is 2. So 0, this 0, and 0 on A is 2. So we put the 2 here. Now you have to see again 2 on A. What is 2 on A? 2 on A is S3. So I write S3. So S3 means shift. So it become shift symbol, right? So A will be coming here. It will be B dollar here. And this 3 should be shifted here, pushed here. Now you have to see the next. What is that? 3 on B. What is 3 on B? 3 on B is it is S4. So S4. So again a shift. S means shift. So $A. This B will be shifted here. Here we have dollar around, and this 4 should be pushed into the stack. Now 4 on dollar. What is 4 on dollar? R3. So 4 on dollar is R3. R3 means what? Which production A reduce? A gives B. So what you have to do again? Reduction is there, reduce is there. So here what happens? A, and now this B is reduced to A. This B is reduced to A. So now it become A. And here it is dollar alone. What you have to do, if in the right hand side, if one symbol means take away one here, and then top of the stack is 3. 3 on this capital A. 3 on capital A is 6. So you have to do 0, 2, 3, and the 6 should be pushed here. Okay. Now 6 on dollar. What is 6 on dollar? See, sixth state on dollar is R2. R2. What does R2 means? Second production, this one. So I have to write A derive small a, capital A. So this means A can be A, small a, capital A can be reduced to A. So here if you see here, dollar A, and this 2 can be now reduced to capital A. And in the right hand side, you have two symbols. Those two things can be reduced from this. And now who is in the top of the tag? 2. 2 on A. So 2 on A is 5. So push it here. 0, 2, 5. Got it? And now here we have dollar. So 5 on dollar. What is 5 on dollar? R1. What is R1? Esterize AA. So now you can understand this AA is reduced to S. Here we have dollar. In the right hand side, we have two symbols. So two symbols can be reduced. Then you have to see 0 on S. What is 0 on S? 0 on S is 1. So push it here. 0, 1. Now we have to say 1 on dollar. See 1 on dollar. 1 on dollar is accept. So completed. 1 on dollar is accept. So now you can say that this string BAB can be derived from this context-free grammar. And this is the step. This is how the input symbol is reduced to the starting symbol, right? So how it is reduced, what are the actions taken? So this is using this parsing table only. It will check whether the given input string is free from the any of the error or not. So this is how parsing will be happening. So every algorithm have a way to do the parsing. So hope you have understood the parsing of LR0 and the SLR1 algorithm. There is one difference between LR0 and SLR is in SLR we just use the follow, and based on the follow we put the reduce. In LR just we simply write reduce everywhere throughout all the terminals. That is the only difference. So this is least efficient. So it is better you should know SLR. And we have other algorithms also we'll discuss in the other video. If you have any doubt, just look at the video once again so that it will be understandable for you. And it is very easy to. Hope you have understand all the concepts. Thank you, ma. God bless you.